Okay, hello everyone. Greetings, aspiring scientists. So, I decided to make another top 10 video today. It's been a while since I did this. I made top 10 most difficult SL chemistry topics. Today I'm going to do HL. So the HL topics can tend to be quite a bit more difficult than SL, as you might imagine. So, let's go through this. I do want to have an honorable mention here. I really thought hard about what are the most difficult topics, and I could easily cut it down to 11, even though I wanted to make a top 10 list. So the honorable mention number 11 is 3.1.12. This is the pH of a salt solution, where you have various different types of salts, various different conjugate acids and bases that are part of a salt being dissolved in aqueous solution, and you have to try to predict whether the pH will be about 7, less than 7, way less than 7, above 7, way above 7, these kind of things. So I don't find this topic too difficult myself, but I know that I have a lot of internal knowledge where I just kind of know how acidic and basic a lot of ions are, but my students, when they get to this part of the IB curriculum, they don't have nearly as much background knowledge about these things, and they find it quite difficult. So you got to kind of know that things like Cl minus, Br minus, I minus, they don't tend to be very basic because they come from strong acids, right? And things like, I don't know, NH4 plus can actually release H plus, make a slightly acidic solution. What else? The weak acids like acetic acid, its conjugate base acetate will be slightly acidic or basic. You got to kind of think about what you're working with and whether it's going to compete with the other anion in the salt that it was with, right? So if you have something like, I don't know, ammonium carbonate, that's like a weak acid and a weak base in a salt. They're going to compete with each other, but the result of that is like not much change from neutral pH 7, right? So a lot of things to consider, a lot of background knowledge that you kind of need to internalize and memorize. But once you do, you tend not to make mistakes on that anyway. 3.1.12. Okay, getting into the real list then. Number 10, I'm going to label as 2.3.5 in reactivity equilibrium. This is the reaction quotient Q. So we spend so much time teaching the equilibrium constant K, and we don't consider really what are we talking about there, what conditions are we talking about. And I try to make it clear to my students that we're talking about a system at equilibrium where it's stabilized, the forward and backward reaction rates of a reversible reaction. But a lot of times when we go to the lab or look at some data or whatever, we're looking at things that are not yet at equilibrium, or where a sudden change has just been made and kicked it out of equilibrium. In that case, what you're dealing with is Q, the reaction quotient. And the reaction quotient has the same formula, really. It's products raised to their powers, which are the mole coefficients, stoichiometric coefficients in the balanced chemical equation. But the number will not be K because it's out of balance for the equilibrium, right? So you can make predictions on how the reaction is going to proceed, how the mixture is going to change. Is it going to make more products or more reactants? With Q, if Q is less than K, there's not enough products. If Q is greater than K, there's too many products, so it will go reverse. The idea behind this is not that difficult, I think, which is why this is number 10, but realizing when a question is trying to tell you to use Q is kind of the difficult thing. On the exam that we just had here in Japan time zone HL chemistry test, they just said like things were mixed together and it was left for 10 minutes, and these are the concentrations that somebody measured. And it's like, why is this different than a K that somebody else measured? And they're trying to get you to think maybe this didn't reach equilibrium yet, maybe it didn't reach there in 10 minutes. And it's asking, what did you actually calculate? You got to think, okay, if this is not at equilibrium, this is Q, it's going to proceed in some direction or another if we give it more time. Quite difficult. All right, moving on. Number 9, I'm going to say is 2.2.16 hybridization. Okay, and the reason this is number 9, this is actually a highly difficult conceptual thing to have in your mind. But the questions that are generally asked about this are quite easy, right? It's just once you remember that tetrahedral things are sp3 hybridized, trigonal planar are sp2, linear are sp, you've kind of got 90% of what you need to know about hybridization to write exams. But when it comes to understanding the textbook or detailed visualizations of orbitals and even like electron configurations, how the orbitals come together, smash together, promote electrons, these kind of things, to produce hybrid orbitals, that's the difficult thing. If there's ever an exam question that asks you to explain that or draw the whole promotion and hybridization process from orbitals, that I think is very difficult. And you really have to have some idea in your mind about the flexibility of orbitals. And you need to know some rules, like the number that you put in is the number that you get out of hybrid orbitals. You need to know what orbitals are remaining if they haven't been hybridized but are still on the atom. A lot of difficult things to visualize and explain in hybridization. Okay. Moving on. Let's go number 8. I'm going to label this as expanded octet. Okay, so this is 2.2.13, expanded octet. The reason why I think this is difficult is it kind of breaks rules that we've just tried to teach students quite strongly. Once you learn this in HL, you can't go back with your SL friend group and think about things the same way anymore. One difficult thing about it is that it only applies to period 3 and lower, so things like carbon, oxygen, nitrogen do expanded octets, something you just need to know. But things like phosphorus, sulfur, they can. And then there's the whole process of counting all the electrons, finding out whether there will be lone pairs on your central atom. You've got a whole new set of electron domain geometries and molecular geometries with trigonal, bipyramidal, octahedral, those sets. You got to consider where the lone pairs are. Are they in the axial or equatorial position? What are the angles going to be? Lots of difficult things to consider. All right, moving on. I'd say number 7, 3.2.11, high resolution NMR. And when I say that this is one of the most difficult topics, I am including basically everything about NMR previous in that. NMR is already quite a difficult topic. It's more difficult conceptually and probably procedurally when looking at spectra than IR or mass spectrum. But especially when you get into spin-spin coupling and splitting patterns and multiplicity and Pascal's triangle, my students just kind of say, what the heck's going on? Why do we have to know this? And I try to tell them that it's very useful, and we don't need to look at very complex spectra in high school in the IB program, but sometimes you can get quite difficult splitting patterns up to quartets, higher multiplets, when there's so many hydrogens around each other in longer molecules, especially with branching. So it's very difficult to read those spectra with all the little peaks and to know what they mean, to differentiate between the integrated area, the peak intensity, the chemical shift. You have to know your stuff if you're going to draw a structure from an NMR spectrum, either alone or with a bit of extra data. So that's why high resolution NMR, number 7. Okay, next, number 6, I'm going to label as structure, 3.2.7. This is stereoisomers in the organic chemistry section. So you start talking about isomers in SL. I think you talk about branched, maybe positional, maybe functional group isomers. But the really difficult isomers to comprehend are in the HL section in stereoisomers. Mainly enantiomers, mirror images, chiral centers, and cis and trans, either with double bonds. Identifying what can be cis or trans is quite difficult sometimes when you've got, constituents that are the same, or you've got ring shapes. There's a lot of things that can change what your answer will be. And even just understanding what mirror images are, how they exist, and how to draw them. all very difficult things. How to measure the purity of an enantiomer with polarized light, very difficult, seemingly out of nowhere, very random things about light and physics that you need to know to really answer these things in detail. So that's why I think stereoisomer is probably number 6 in difficulty. All right, moving on then, 3.2.9 in reactivity. This is SN1 and SN2 mechanisms of substitution, nucleophilic substitution. So there's a lot of things going on here. You got to know, whether it's going to be SN1 or SN2 based on the position of the halogenoalkane. Usually we're talking about halogenoalkanes where a nucleophile comes in and kicks out a halogen anion. So primary versus secondary, stability of carbocations. You have to know how to draw the curly arrow mechanism. Usually there's like 3 little stages you have to draw in there and show where electrons move around. You have to get the charges right, transition states right, intermediates right. You have to know effects of the leaving group, the solvent, all sorts of things. You have to know that secondary carbons can do either SN1 or SN2, and usually tertiary do SN1. You have to know how they relate to rates, unimolecular versus bimolecular, very difficult. All right, next, number 4, I'm going to label as 1.2.5 in reactivity. This is Born-Haber cycles. So you probably get to enthalpy and you see Q equals MC delta T. It's pretty easy. You maybe do adding chemical equations together, canceling things out, adding up the enthalpies. You get those enthalpies down. It's pretty easy. Triangle diagram. A lot of my students don't like that, find it quite difficult. And then HL students get here to Born-Haber diagrams, which are like an extension of the triangle diagrams. I actually prefer a full Born-Haber diagram to a triangle diagram, because in a Born-Haber diagram you can really get things laid out with arrows along a whole sort of energy spectrum of your page, where down low is low energy things, up high is higher energy things. Arrows that go up show endothermic processes, arrows that go down show exothermic, where the products are more stable, less energetic. But some reactions that I've seen in textbooks and, on practice question websites, even on exams, are pretty crazy with how you need to draw the processes. You can have arrows going up and up, then down a little, up a huge amount, and there's this whole rectangular cycle. Sometimes it doesn't even look like a rectangle depending on how you draw those arrows and where they point. But it's really hard to know where certain sets of products and reactants fit in the cycle, especially if you have to draw it from scratch sometimes. A lot of exam questions will have it laid out already and you just answer questions about it. But when you have to draw it from scratch, very difficult to get all the arrow directions, the signs of those enthalpies right. Quite difficult. Next, number 3. We're in top 3 now. This is 3.1.13 in reactivity. This is HL pH curves. So in SL, you see, I think, the pH curve of a strong acid with a strong base. Looks pretty nice, a nice sigmoid curve with that equivalence point going through 7. It starts either acidic or basic. It finishes either acidic or basic, depending on what you're adding to what. When you get to HL, you have to start considering mixtures of strong and weak. So weak acid titrated with strong base, strong acid titrated with weak base. Any combination of those things, weak with weak, you have to have in your mind what the curve looks like, and you need to know where specific points on that curve should be. Where will the equivalence point be in terms of pH and in terms of volume on the x-axis of titrant? Where will the buffer region be? Where is the pKa or pKb on this curve? What kind of pH is it going to start and finish at? So many things to consider, and usually drawing it is worth 3 or 4 points, and you have to try to get them all. Also, just knowing the weak acid-weak base curve is strangely shaped with no real vertical sections is quite difficult, and something you just have to know and memorize. Yeah, I'd say that HL-pH curves definitely deserve top 3. Next then, I'm going to say 3.1.17, but I also want to include 0.16 in there from reactivity. This is buffers from acids and bases. So there's several layers to this. You have to understand what a buffer is, how it's made, how to calculate its pH, how can it exist in mixtures of various things, where does it appear on the pH curve, lots of things to know about buffers. There's like 3 or 4 different ways to make it, right? You can mix solutions, you can mix salts, you can do the titration, and you've just got to know that it's when you have high concentrations but nearly equal concentrations of a conjugate acid and its conjugate base together. And you have to know that it creates a resistant solution that is resistant to pH changes. And it will basically work until the acid or base, conjugate acid or base, has been too neutralized or removed from the solution, right? So lots of things to know, and people, sometimes learn some of those things, but don't really even know what a buffer is by the time they get to the end of it, kind of forget what it is. And you also need to be able to write equations for how the buffer works. Pretty much on every exam, they'll ask you, how does this absorb excess protons or excess OH minus? You have to draw it with the conjugate acids and bases, the reactions. Very difficult. All right, that brings us to number 1. Drum roll. I will say the most difficult HL topic and the most difficult topic in all of HL chemistry, or chemistry in total, is 3.2.15 in reactivity. This is electrolysis of aqueous solutions. For so many reasons, when I have one more class before the end of IB exams, my students ask me, can we please do this? Because I just can't get the questions right when I do the practice questions. And I also struggle with these a lot. I'm not an electrochemist by any means, but I think I do understand the basics of how this works. So you learn in SL, basically you can have electrolysis of molten salts, and you get non-spontaneous reactions. You push them against what is spontaneous by inputting energy. But when you get to aqueous solutions, that could happen, but it needs to compete with water. Water itself can be oxidized or reduced. It can make oxygen gas, H+, lots of different possible products, gases, ions, OH-, whatever, depending on what your data book tells you. And your data book gives you reduction potentials, which you sometimes need to use as oxidation potentials. If it's being oxidized, you need to reverse it, consider the sign, possibly flip your series to know what's more reactive than other things. And then there's this whole thing of like, what's it called? When over voltage, that's what it's called. It's kind of like the activation energy of electrochemical reactions, where you do everything right, you calculate it, okay, it's going to be this is the most positive E cell, it's going to happen spontaneously, but it's like, no, just happens like chlorine and water have over voltage problems, where the opposite happens in this case. You just need to know that. Very annoying to know, but if you do study some good textbooks and do practice questions, pass exams, it's not impossible. Okay, you got to consider what's oxidized and reduced, and if you're trying to calculate E cell, remember, always use the reduction potentials where you do the cathode electrode minus the anode. Never use the oxidation, even though one of them is being oxidized. Just a lot of little tricks you need to actually get any right answers, and these questions can be worth a lot of points on exams. All right, so that's the list. Hopefully you enjoyed. Watch out for those top 10 most difficult topics if you haven't done them yet, or if you're trying to review for them. Get the help you need. I'll be making videos on these when I'm done SL, probably later in the year. All right, thanks for listening. See you next time. Goodbye.